Today I'm going to talk about models of words, and in the reading you read about the word embedding models and everything. Some of the content of the I'll briefly summarize the content of the reading, and when I do, I'd like people to ask any questions that they had at the time. Hopefully, it will help you remember any questions you had. And then after that, I will talk about some more advanced topics that were not included in the required reading. So. Before thinking about this, I think what we should think about is what we would like to know about words for the purpose of NLP applications or computational linguistics where we want to examine something. And there's lots of different things. Number one is, are they the same part of speech? Like, do they have the same syntactic function when in a sentence? This could be useful for things like machine translation where you want to get the structure right. Obviously for part of speech tagging. If you know the part of speech, then that's useful there. Named entity recognition, etc. Another thing is, let's say, do they have the same conjugation? Do they have the same word form? And the same word form indicates a lot of things like part of speech, but also case or gender or whatever other thing in languages that express those. Another thing is, do the two words mean basically the same thing? So do they mean the same thing minus conjugation, or are they plurals of each other? Are they synonyms, etc.? Or possibly, do they have some other semantic relation? So do they are they in an is-a relation where one is a type of another? Are they part of? Or even more complex things like went to school at. So where did Barack Obama go to school? Where did Obama go to school? And if I remember correctly, Occidental College and Harvard or something like that. But there's and you might want to know those for question answering or whatever else. And an important thing before we talk about neural networks is to think about manual attempts to do these kind of things. One manual attempt is WordNet. So how many people have used WordNet in your research in some way? So that's a good, maybe 1/3 of the class. Probably if I asked this like 5 years ago, it would be 2/3 of the class, because this has had a huge impact on how people do things. And what WordNet is basically, it's this large database of words, including parts of speech, semantic relations like is, part of, antonyms, etc. And this has been an extremely major effort. It was a big effort to develop. Unfortunately, on the WordNet page, now they say we cannot respond to emails about improvements to WordNet anymore because we don't have funding to do so. And it's a very real problem. These big projects, they take a lot of time and money to create. So the idea is we would like to create something that's almost as good as WordNet, maybe better in some ways, worse in other ways. But is it more complete and with less or no effort? And the answer to this is word embeddings, like you read in the reading. So they're continuous representations of words. Within the word embedding, they have features of syntax, semantics, etc. So like WordNet, they encode parts of speech. They encode is-a relations. So for example, element 1 might be more positive for nouns. Element 2 might be more positive for verbs. Or element 2 might be more positive for animate objects. So if something's a living being, which is one of the categories in WordNet, then maybe this is expressed by element 2, for example. Element 3 might have no intuitive meaning whatsoever, or it might not. You might not be able to know what it means without looking at some of the other elements. And these are cool. This is an obligatory slide that you've seen in every talk about word embeddings ever, which is, so you take the word embedding space, you have something like king and queen. You take kings, you subtract king and add queen, and you can get queens. So you can get the plural of things, or you might be able to get female versions of other things. And you might be tired of seeing this, but this is a really big thing, actually. This is something that you couldn't get from WordNet. Like, what is the female version of king is not included in WordNet. So I think this is what makes these really exciting, I guess. So are there any questions so far? Pretty elementary. Yeah.
So we said this is some latent representation and some dimension might correspond to color or something like that. Is this actually true? Do some dimensions independently correspond to certain things that we can make sense of, or is it just like a hand-wavy thing to explain?
So that's a good thing. In the answer in general is no. But it can be yes, and I'll explain about that at the very end of the talk this time. Anything else? Okay. So how do we train them? The kind of default way of training them is to initialize them randomly, and then if we have some task that we're interested in, we train jointly with that task. Another way is to pre-train on the supervised task, like part of speech tagging, and test on another. This is less common than initializing randomly, and then it's also less common than the third way, which is pre-training on unsupervised stuff. This was explained in the reading materials. The reason why it's common to do the first and third is because they're easy and they don't require labeled data. So if you have lots of unlabeled data, you can do the third one. If you don't have any data, extra data, you can do the first. But the second one requires that you have lots of labeled data in some related task. And so it's a little bit less common than the other. Oh, the quiz, yeah, sorry, go ahead.
If you do have labeled data, should you still favor a random or unsupervised querying, or?
That's a good question. So the question was, if you have labeled data, should you favor an unsupervised? The answer is it depends on the size of it depends on the size and the quality of the data. So supervised tasks tend to be better. But unsupervised tasks, you can get lots more data. So it's basically a trade-off where you can't say. There was a nice paper on sentence embeddings, which I'll talk a little bit later, which showed that despite the fact that you have lots more unsupervised data, by training on a supervised task like natural language inference, you can get better embeddings. So there are definitely cases where if you have lots of supervised data, it can work. Yeah.
Does it necessarily have to be a related task that if it's only supervised?
So the question is, does it have to be a related task? And if it was completely unrelated, then probably it wouldn't help. But I think in NLP, there are very few tasks that are completely unrelated. Like literally, there's absolutely no shared information between them. So you'd probably get something, but the more related they are, the better. Okay, I will move on to the next one. So I will blow through this very quick because it was in the reading materials, but if you had any questions that came up during the reading materials, I'll be happy to solve them. Not solve them, but sorry, answer them. One thing that was in the reading materials, but I didn't feel was put out really clearly there, is the difference between distributional and distributed representations. And I actually didn't understand this very clearly for a while. But they're completely different things. And distributional representations are basically representations that are calculated based on the distribution of the words in a corpus. This is based on the distributional hypothesis that distribution of words indicate their usage. If you wanted to create non-distributional word representations, you can. There's actually a paper called Non-Distributional Word Representations, written by Manal Faroukhi, who was at CMU at the time. And the way they created it was based only on lexical resources, such as WordNet, et cetera. So they didn't use the distribution in corpus statistics and just used that. So that's the difference between distributional and non-distributional. Then distributed, the opposite of distributed is local. You actually don't hear people say this very much, but if you read a neural networks paper from the 1990s, they talk about this all the time, distributed and local. And a local representation is basically a discrete one-hot representation of a word. So you represent the word as a one-hot vector, and you don't have any like low-dimensional information sharing between the words. So another thing that was not in the reading, I guess it was in the reading, but distributional representations appear in their context. What was not in the reading is a really good example of this. So to create an example, I created something kyc.py. Does anyone know what kyc is? Anyone take a linguistics class? Whoa, lots of people shaking their heads. Okay, it's called keyword in context. It's keyword in context. And what a keyword in context is, actually people in corpus linguistics use this a lot to kind of examine how a word is used. And you show all of the examples of the word and you show a context window around them. So in fact, people in corpus linguistics do exactly the same thing that word2vec does. They look at the 10 words surrounding the word and try to guess its usage. And if you do it for Pittsburgh, you get something like Unk Communications Pittsburgh acquired Unk & Co. Investment Management Inc., a Pittsburgh firm, Allen's Pittsburgh firm, etc. And then if you do Cleveland, you get a Cleveland Bank, a Cleveland Merchant, Cleveland Districts. So you can see they both tend to be followed by things like firm or branch or bank or merchant or districts. So you can see that it kind of makes sense that these words are considered similar. And if you want to try it yourself, you can run kyc.py on your favorite corpus, and it will output this for you. So there's a lot of different methods to create representations. Count-based methods create a word context count matrix. Count the number of co-occurrences of the word in context. Rows is words, columns is context. Maybe weight with something like pointwise mutual information, and then maybe reduce the dimensions with SVD, and then measure the closeness of something with using cosine similarity. So this is kind of the recipe that people use for count-based methods all the time. Yeah.
What exactly do you mean by context? Like, is it actually mapping of the words irrespective of order, or how does it work?
So that's a good question. So what it would be basically is, what did I say? Rows were words and columns were context? Yeah. So the row is the word that the question was, what do I mean by context? And the row is a word, so maybe the row would be Pittsburgh. And the column would, the second row would be Cleveland. And then the column would be something like, let's say we were using exactly this context. The column would be the count of the number of times each of these words occurred within a surrounding 8-word window. So in just this example, maybe you can count you can count the word a some number of times in the first one, I guess 1. So a would be 1. And then you have a also, or you have a twice in the second one out of all the words in that window there. And then you would count that up for your entire corpus, and that would be like your context counts,
so
essentially.
Would you be counting communications, sorry, okay, say Allen.
Mm-hmm.
So you're just counting Allen Pittsburgh as one? Or do you want to say Allen apostrophe S is that context?
So you can design your context any way you want.
How do you, like, this would be a very sparse
Right. This will be a very sparse representation, but it's still actually pretty good, even if it's that sparse, just because if you have enough instances of Pittsburgh and Cleveland, kind of their vectors will start looking similar, right? But it's sparse, and the reason why it's sparse is because it's sparse, we do dimension reduction using SVD or something like this to make it dense. And that's how count-based methods normally handle this, yeah.
If you're maintaining only counts of your contexts in the window, if we were to also try to include order in this matter, how would the counts anyway help?
So if we also wanted to consider order in our context, how would we do so? And the answer is basically we would not only count the number of times it occurred in this window, we'd have counts specifically for each position around us. So we might have the number of times this word appeared to the right and the number of times this word appeared to the left.
So basically your columns is for every the position cross, the times of position cross.
Right. So your rows here would become 8 times larger if you had an 8-size context window, which is actually why people don't do that most of the time. It become unwieldy. I'll actually talk about designing contexts a little bit later, and that's actually really important for these models. Anything else? No? Okay. So that's how we do count-based methods. Prediction-based methods instead try to predict the words. So this is like the SIBO or Word2Vec. And word embeddings are the byproduct here of doing the prediction. So one important thing to remember is that actually the first word embeddings were just a byproduct of language models. So language modeling is useful in itself in that if we can calculate the language model probability, we can do things like re-ranking for machine translation or speech recognition or something like that. But while we're training our language model, we also learn these parameters. We learn the parameters that we use to look up a word embedding. We also learn the parameters in this matrix here that we use to calculate our softmax. And these are basically word embeddings. These are things that we can use. And this was covered kind of briefly in the reading, but basically, if we don't need to calculate the probability of the sentence, we can come up with other methods. And these can move us closer to the contexts that are used in the count-based methods. So count-based methods always use information on the left and the right because, of course, information on both the left and right is useful. While language models generally only use things on the left because we need to multiply probabilities together according to the chain rule to get a valid probability for the sentence. So by relaxing the constraint that we have to calculate valid probabilities, we can use information on both sides. And these kind of models drive Word2Vec, et cetera. So the SIBO model, basically, we look up the context. We add all the context together into this. And we calculate some sort of score for all of the words and take a softmax to get the probability. And this is basically our model. So these red things here this vector here is kind of the context embedding. And each row in this matrix here is the word embedding in the SIBO model. So this kind of makes the connection to the neural language models. Neural language models are the same as this model, except they only consider the context on the left. And they also have some sort of nonlinearity in there. So the SIBO model doesn't have a nonlinearity precisely because it wants to have those kind of nice linear connections between the words. So yeah, that's the loss. And I have an example of doing this, which I can show you very briefly. So the way it works is you and as with all of the examples here, I'm just going to show you very briefly, and then you can go back and look at the code carefully at the end. But if we go down, we have parameters where we have parameters to look up our words or look up the context at each position, and then we have parameters to calculate our softmax. And then we create a padded sentence. So when the context on the left or the right goes off the edge of the sentence, you basically pad the sentence on that side. And then our loss is the sum of the embeddings on the left side and the embeddings on the right side. and then we calculate this times the matrix, and we calculate a loss here. So that is the that's the sum, and everything else is kind of like the language modeling part. I see a question, and I will go to the question. Yeah.
So even in this case, you're essentially in continuous dialog, you're essentially trying to find out the likelihood that a particular word will appear, right?
Yes.
Either like in the center if it's like scriptgram or the next word.
Mm-hmm.
But then you say that these methods are bereft of the need to calculate the probability of the sentence.
Mm-hmm.
The same thing?
So these methods cannot calculate the probability of the sentence, and the reason why. So the question was why can these models not calculate the probability of the sentence, right?
I have a feeling that this is what they're trying to do itself.
Yeah, so they're not actually trying to calculate the probability of the sentence, and the reason why they can't calculate the probability of the sentence is because in order to calculate the probability of the sentence, you have to be able to define the probability according to the chain rule. And the way the chain rule works is basically the probability of x, or let's say x1 to xn, is equal to the product of the probabilities of xi given x1 to xi minus 1. And the reason why this can't be used here is because you're only allowed to condition on the previous words when you calculate this probability. But this is also conditioning on the future words, and that's not allowed according to the math of a language model. So is that clear? Yeah.
Also, it's not a valid distribution that this algorithms, right? These are just scores. I mean, you have to take a softmax over all possible scores to get to a valid distribution.
So that's getting a little bit ahead of this. So the model I described here, this would give you valid scores. So would a lot of other methods. So like noise contrastive estimation was mentioned in the reading. That would also give you a valid score. So I'm going to talk about ways to make it faster later. But I wanted to describe the model and its connection with language models. So here I'm still talking about using the softmax directly, and this would be okay. So just to put it in context, Word2Vec is kind of two things. Word2Vec is a model and an efficient estimation algorithm. I'm talking about the model right now, and I'll talk about the efficient estimation algorithm a little bit later. Any other questions? Not? Yeah.
On the language model,
Yeah.
there are two types of embeddings, right? In the input layer, the embedding layer,
Yep.
and the rows of the weights.
Yep.
What is the relationship between these two different embeddings?
So that's a good question. So last Thursday, I talked about the relationship between the embeddings in the input and the softmax, and said we could tie them together, right? We can make them basically both be the same matrix. And that's very good for language models in general. When language models have nonlinearities and you can combine the embeddings together because it reduces the parameters of the model. And because you have nonlinearities, you can combine them together in the appropriate way to make them conducive towards predicting the next word. It is a bad idea to share the context embeddings and the word embeddings here because you're using a linear model, and this linear model is not expressive enough to basically convert these four things added together into something that would be useful for predicting this. So I guess long story short, you can tie embeddings in, you can tie the embeddings together in the language model, but you almost never do in these models here. Okay. So the skipgram, basically you look up and you calculate the probabilities, and you try to calculate the probability of all the surrounding words. So it's kind of the inverse of the SIBO And I have example code for this, but you don't need to look at that now. Yeah.
I'm sorry. The reading made it sound like you split the context, so you split your k-word context into k different contexts, and then you are still just trying to predict the word from the context, not the other way around. Is that wrong?
Is that?
Yeah.
Oh, okay. My understanding was different, but
In the
I
reading,
might
it
be.
appears to be the case that we are
Okay.
using each of those words to predict the word,
Okay.
and the context words are independent of each other.
Okay.
But even in the paper and your slides, it's this.
Okay. I believe this is correct, but I am not very confident. So either the reading is wrong or I am wrong. So I'll have to go back and check. Is anyone familiar with word embeddings? Able to say with confidence that one is or the other is correct? Is the SIBO or is the skipgram model basically predicting all of these words in the context, or is it or is independently, or
Together.
is it together? But so it's predicting the context, right? And the book was apparently made it sound like you were not predicting the context, but you were instead you were predicting the center word, but doing it independently. So there's a possibility that the book's wrong, and I'll go back and take a look at that. Okay. So I will move on to the next part. So there's count-based methods, which have been around for forever. There's prediction-based methods that have not been around as long, but people are using them a lot now. There was a paper called Don't Count, Predict, which is basically saying that prediction-based methods do way better for word embeddings on similarity tasks and everything. And it was written by Marco Baroni, who was a person who really liked count-based methods. So that the story behind that paper was he was trying to show that count-based methods did just as well as prediction-based methods, and he wasn't able to do so. So he changed his way of thinking that basically the prediction-based methods were actually pretty good. And then there's also a few influential papers that tried to disentangle the various embeddings and say that basically there's a really strong connection between the objectives that each of these are maximizing. For example, the skipgram objective is equivalent to matrix factorization with PMI and a discount for the number of samples. So basically, you weight this matrix with pointwise mutual information, and then you subtract minus log k. To do this. And sampling I'll be covering not next time, but next time with respect to the with this. But the important thing here, I guess, is that there's a very strong correspondence between word-to-vec and matrix factorization-based approaches. One other approach, this is basically a count-based approach, or it is a count-based approach, but it's used very widely now, called GLOVE. I think people maybe have used this in your work for something or other, because it's maybe the second most popular to word-to-vec. So basically GLOVE is a matrix factorization-based approach, and it's motivated by ratios of probability of word given context probabilities. And they have a really nice example. This is a very good paper in general, by the way. I highly recommend reading it because it's very logical and explains why they do things in a very concise way. But basically the idea is, let's say we have ice and we have steam, and we want to know what the difference between ice and steam are. And what we can look at the probability of solid given ice, and we can look at the probability of gas given ice and the probability of solid given steam, the probability of gas given steam. And you can see that the probability of solid given ice is way higher than the probability of solid given steam. And the probability of gas given steam is way higher than the probability of gas given ice. And then the more neutral ones are kind of about 1. So the idea here is basically that these ratios are very indicative of kind of important words that are important to this particular context. Yeah, there you go. And they have a very nice derivation from this starting point. So their starting point are these kind of probability ratios. And then they have a whole bunch of things that they want this objective to satisfy, like it's meaningful in linear space. So you get the nice linear relationships like king, queen, etc. And that you can take dot products, that there's invariance between the vectors in the word and the context. So this is something that word2vec, for example, doesn't have. So this is more like the tide representation. And then also being robust to low frequency contexts. And in the end, you get this objective function, which is basically that you want to do matrix factorization, where you take this word count matrix, or sorry, the probability ratio matrix, and you optimize this objective here, where you're taking the dot product between things, adding some biases, and taking the log here. And it's a kind of squared error loss. I won't go through the details here, obviously, but if you look at the paper, it's very clear in laying out how you get from here to there. So are there any questions? No? Okay, so the next thing, this is what we were talking about before. So which contexts do we use in our word embedding model? Context has an extremely large effect. And it's kind of funny. There's a method called Brown clustering. Have people heard of this before? Yeah, some people. So Brown clustering is basically this method that was made in like 1991 or something like that, in order to kind of guess syntactic relationships between things. And Brown clustering works on a small context window. It looks at only the surrounding words. And because of that, you get things that are kind of syntactically similar and also maybe semantically similar. So you get lots of ing words in the same class, etc. On the other hand, if you take a large context window, like 10 surrounding words or the whole document, you tend to get things that are more semantic-based or topical. So you tend to get, water and steam tend to be close together, or whatever. Or like specifically for things like verb, love, loved, and loves will all tend to be relatively close together. There's also a mention of context based on syntax in the paper where they show that this allows you to get even more syntactical things. But the reason why I mentioned Brown clustering is I didn't realize this until about a year ago, but if you go back and read the Brown clustering paper, they say, oh, and by the way, we also trained semantic clusters by making our context bigger. And look at them; they're kind of nice. So I totally didn't realize that in that paper they had also realized the small context window, large context window thing. So I think the moral of the story is you should go back and read all of Peter Brown's papers on on this, because he had lots of good ideas. Okay. Yeah.
What did you mean by same inflection group?
Oh, so this is kind of like what I mentioned before. So like ing words tend to be grouped closer together. Words with the same like conjugation, I guess. So inflection's another word for conjugation. Okay. So evaluating embeddings. One once we've trained embeddings, as I mentioned before, these embeddings are usually trained on a task that we don't really care about. So we don't really care about whether Word2Vec is good at predicting the central word based on all the other words. We want to evaluate these based on their use for something else other than the task that they were trained on. So one important thing is intrinsic versus extrinsic evaluation. I think people have heard these terms before, but if you haven't, they're very useful. So intrinsic is basically how good is it based on its features. So if you look at the features of the word embedding itself, how good is it kind of on its own? And extrinsic is how useful is it in downstream tasks. So how much can it help us do something downstream, usually in a much more complicated system. Also qualitative versus quantitative. Qualitative examine the characteristics of examples, quantitative calculate statistics. So the first thing you can do for qualitative evaluation is just visualize things. So this is the kind of thing that gives you the really beautiful pictures that we never get in NLP papers. So NLP papers, we always lose out to computer vision because computer vision, they're just like, wow, look at the thing I generated with my GAN. And it's like, look at this beautiful video of celebrity faces merging into other celebrity faces. And unfortunately, we can't do that, but we do have our word embeddings. So we could get things like, so number one, word embeddings are 512 dimensions, right? So we can't easily visualize 512 dimensions. So the standard practice is to reduce the dimensionality to 2 or 3 dimensions, maybe. And you can do that. So the most standard way to do this is with something like principal component analysis, PCA, which is a linear projection from your high dimensional space to this low dimensional space. And you get these nice lines between things that represent semantic relationships. And you can see that it's useful. Another popular thing to do is nonlinear projection. So nonlinear projection, the most famous one is t-SNE. So t-SNE is a type of nonlinear projection that basically attempts to group things together with a nonlinear projection that gives them that makes the word embeddings that are close together in the space have a high probability according to a Gaussian, or it makes things that are close together in low dimensional space have a probability in high dimensional space. Sorry, I apologize. I read this paper like one year ago, and I forgot which direction it goes to. But that's the basic idea. And the reason why people use this is if you look at something like PCA, this is just a mapping of digits, of the MNIST digits, if you're aware of MNIST, into a low dimensional space. And if you do it with something like PCA, you get things that are kind of separated, but they're not really like well separated in the space. On the other hand, if you do it with t-SNE, you get these very nice clusters that correspond to each of the digits. So the red one is one digit, the green one, their green one's another digit. So the idea behind t-SNE, why you would use t-SNE instead of PCA, is it's a better visualization of things that are close together in the space as opposed to a visualization of actually their linear relationship. And I have code to do this. I think I'll skip this skip the code in the interest of time. Yeah.
So we made two distinctions. One was like intrinsic versus extrinsic, and one was
Yeah.
qualitative and quantitative.
Yeah.
So what are some good intrinsic evaluations, like mostly based on features?
So the intrinsic evaluation measure, it's a kind of tough distinction to make exactly, but basically in my mind, an intrinsic evaluation is how good is the word embedding itself, without respect to how well it works in the task that we actually care much about. So I'm still talking about intrinsic evaluation, so let me go to the end and talk about some extrinsic measures, and then you can agree or disagree about whether they're actually intrinsic or extrinsic. But in my mind, this is still intrinsic evaluation, and it's qualitative because we're looking at the...
I read somewhere that if you tweak t-SNE enough, you can see whatever you want. So, I mean, is there some truth? Is it true? How reliable are these visualizations actually?
Yeah, so that's actually my next slide. So, t-SNE visualization can be misleading. So there's a nice paper on distill.io, which is this kind of like visualization-oriented journal about machine learning. That has a JavaScript app where you can actually tweak the various parameters of t-SNE and see the different results it gives you. So if you look this up, I think the link is on the class website. And basically, it has several parameters like the perplexity, the number of steps that you optimize the function, etc. And the answer is, if you change the setting, you can get whatever you want. So this original one here is just kind of these clusters. And so you would expect something that looks a little bit like the one on perplexity 50. But if you change the perplexity and change it to 2, you get things that are scattered all over the place. If you turn the perplexity up to 100, you get things that are kind of like scattered all over the place, but not in clusters at all. And then there's a sweet spot for the parameters of t-SNE. And it's also similar, like let's say we have 2 lines. This should be the easiest thing ever to visualize, right? And instead we get like a helix, which is pretty magical to me. But, so one thing, if people say t-SNE visualizations, one time I was working with a student on a project, and he came with a t-SNE visualization, and he had these nice lines drawn between points in the t-SNE visualization, and that's not something you can do. You can't draw lines like vectors between things in a t-SNE visualization because the vectors don't mean anything because it's a nonlinear projection. That being said, it is a better way of visualizing things that are close in high-dimensional space, so it's something that you can have in your toolbox of things that you can use. Oh, actually, never mind. I do have a citation for intrinsic versus extrinsic. So intrinsic evaluation of embeddings. Here are some things that Schnabel et al. Said were intrinsic. So I have a citation, so it must be right. Just kidding. You can still question this. But the things that I categorized here that I tend to agree with is relatedness. So the correlation between embedding similarity, cosine similarity, or whatever other variety of similarity, and the human evaluation of similarity. So if two humans say these words are similar, and the word embedding space also says these words are similar based on their cosine similarity or something, then that's probably a pretty good indication that you have a good word embedding space. Other ones are analogy tasks. So analogy task is like the king-queen example. So you try to solve things where A is to B as X is to Y, where you leave one of those out. And so you have like king is to queen as man is to something. And if you can solve that properly, then you get a higher score. Another thing is categorization. So you create clusters based on the embeddings. You cluster them together based on a clustering algorithm. And you measure the purity of the clusters. And one way you do this is by doing intrusion tests. So intrusion tests are basically you add one thing that's not in the cluster to the cluster, and you can see how many times humans actually identify that correctly. So if your clusters are very good, then you have the US, Japan, China, India, and then you add banana or something like that, and they'll be able to identify banana 100% of the time. And how well they can do it on that is one of them. There's another one, selectional preference. This is a pretty minor one, but it was still cited in the paper, which is determining whether nouns and verbs tend to go together as arguments. So extrinsic evaluation, in my mind, is basically using the word embeddings in systems and seeing how well the systems do. So you can initialize your system with the embeddings and then start training the system. And because you initialize with better embeddings, your system often converges to a better place. Another way is you can concatenate the pre-trained embeddings with the learned embeddings. So you have, every time you look up a word, you have the pre-trained embeddings. Then you have your looked up embeddings. These both have their advantages and disadvantages. Does anybody have an idea what an advantage of each of them would be? What about the first one? Yeah.
Well, so would you be training starting from those embeddings? Like, would you freeze those embeddings, or would you?
Oh, so another way is you can freeze the embeddings and not learn them at all. So yeah, actually, I should have added that on top. So freeze the embeddings, initialize with the embeddings, or concatenate the embeddings. But usually you initialize and then continue training. Yeah.
For the first one, you can basically have a better generalization maybe.
Uh-huh.
You've learned embeddings in a common space, but you may not encounter all those tokens in your common training.
Uh-huh.
So,
Yeah. So the answer was that you can generalize better because when you get a new word, you can you'll be able to handle it even if it wasn't in your training data. I think that's true in general for these, and actually I think the second method is potentially better for that. And the reason why I think it's better, I have a little bit of empirical evidence, but not a whole lot. But one of the problems with initializing with embeddings is actually it goes in and changes the embeddings. And your embedding space is in a new space that is different from the one that you had pre-trained, only for the things that were in your training data, for the task that you're interested in. So suddenly all the things that were in your training data are in this new space, and then the ones that you haven't seen are still in the old space. So it leads to a disconnect. So concatenating ensures that these will always stay in the same space, and then these ones can be updated in any way you want. I'd say the main difference between or the main advantage of initialization is this adds more parameters to your neural network, where you basically have to double the parameters. And these ones don't necessarily get learned quite as well because these ones are really strong in the beginning. So it becomes a little bit harder to learn your model.
When you say concatenate, do you mean keeping one fixed and the other one only changing?
Yes, exactly. Yeah.
Then what are you evaluating on? What metric? Say if you do concatenate tree.
Okay, so this is extrinsic evaluation. So you train on task loss. So parsing, machine translation, dialogue, whatever task you want to do.
And it should perform well. If you concatenate it with pre-trained embeddings and it performs well, you say that those learned embeddings are good.
Yes, that's extrinsic evaluation.
But would that not lead to like an overfit concatenated embedding in general?
Actually, I realized I should repeat the question. So the first question was basically, are you saying what is the measure that you use here? And the measure you use is task loss, like machine translation or dialogue or whatever. Then I guess the second thing was, is there danger of overfitting? So yeah, there's danger of overfitting, but if you have good embeddings, you're less likely to overfit because it will be easier to learn. And when things are easier to learn, in general, when things are easier to learn, it's harder to overfit. Yeah.
Would you want the pre-trained embeddings and the learned embeddings to be in the same space so that there's similarity between words that were pre-trained and then that's in the learned embedding as well?
Wouldn't you want the pre-trained embeddings to be in the same space with the learned ones?
What I would understand is you want to continue to train them to your task.
So yeah, it's the other alternative is to fix the embeddings and not train them. That is usually worse. It's usually better to initialize and then continue training. because you do want them to be tailored to your task.
In the concatenation case, you keep the pre-trained embeddings fixed.
You keep the pre-trained embeddings fixed, but you also have other embeddings that you could learn, and these are the ones that allow you to learn the task-specific stuff. So that's the motivation for concatenation.
This is better than having all of them learn.
This is often better, yeah, but it makes it a little hard.
So what happens to the tokens which aren't seen in the actual task at hand? Like in the case where you have pre-trained embeddings, and then you have some tokens which you do not see in the task, then you cannot learn the new embeddings for them. So how do you work with that?
So the question is, what happens to the embeddings that you don't have in your embedding, in your library of pre-trained embeddings? In the initialize case, you just initialize them either randomly or to the average of all of the words. So if you initialize them to the average of all of the words, they look kind of like, words, I guess. And then you continue training, and because you continue training, you'll end up getting embeddings. If you have completely unknown words in the test set, then you'll have to have some sort of unknown word token, or replace unknown words with the average of all the words or something like that. So, yeah.
In the reading, actually, there's another way, you can linearly add the two. So do you know, in practice, whether the concatenate one is better or?
So you can also add them. Well, linearly adding them together is actually pretty close to initializing with them. And
you can fine-tune the differences.
And if you don't so it's also mentioned in the book, but if you don't regularize, if you don't add any regularization, they're equivalent. Fine-tuning does tend to help, but or regularization on the difference does tend to help a little bit, but not a huge amount in my experience. But it's definitely something that you can try. And concatenating adds parameters, but it tends to work better in my experience. Okay. Yeah.
Sorry, just to clarify, when you're concatenating, are you effectively then freezing the pre-trained embeddings and still learning the other embeddings?
So the question is, when you're concatenating, TA, could you close the door? This is a class in the School of Computer Science, not the class in the School of Drama. So you will have to listen to me talk instead of listen to them sing. Okay, so concatenating is essentially freezing. Yes. Okay. So okay, I will move on. So how do I choose embeddings? How do I choose which embeddings I want to use for my task? Basically, there's no embeddings that work for everything. So there's no best answer. In general, ones that are trained on bigger data tend to be better, which is maybe not surprising. There's a good examination of this in the Schnabel et al. Paper, where basically they try a bunch of different things. And the SIBO embeddings that they tried worked pretty well on most of their intrinsic metrics. But then if you tried them on extrinsic metrics like F1 chunking, on chunking or dependency parsing, the Goldberg and Weston embeddings worked better. So basically it depends on whether you want syntactic embeddings or semantic embeddings, et cetera. So basically there's no real answer, and you kind of just have to try. That being said, the big ones trained by popular libraries such as GloVe or FastText or Word2Vec are probably pretty good places to start. Another good thing is to follow the previous work that did a similar task as you, because they probably did the same thing, and they probably found the best one. When are pre-trained embeddings useful? Basically, the answer is when training data is insufficient. They're most useful for things like tagging, parsing, text classification, because these are all hand-labeled data scenarios where we never have enough data to train our models. They're less useful for things like machine translation, because machine translation, we can get a relatively large amount of data compared to the other tasks. Still, they are useful in some situations. basically not useful for language modeling. And the reason why they're not useful for language modeling is because you can get just as much data for language modeling as you can get for training word embeddings. So they might help you converge faster, but they probably won't help improve your accuracy very much. Yeah.
So for say example, take the example of the machine translation task.
Mm-hmm.
If you run fast text before that, get embeddings on the same data, and then use that to initialize a network versus just randomly initialize a network and let the machine translation run, is that going to be any different? Or
So in my experience, that will give you very little difference if it's the same data. If it's a lot larger data, then it can make a big difference. There's one qualifier there, which is that fast text is using a more sophisticated model for creating embeddings than you normally use in machine translation. So you could get a little bit from the fast text model being a better model, I guess. Yeah. Okay. So I talked about a lot of kind of topics in word embeddings, and in the end, I'd like to finish up with ways that people have proposed to improve embeddings. And like for a couple years, there were so many embedding models proposed that there's no way I could cover all of them here. So I'm just going to cover a few of the kind of high-level topics that people have thought about. I heard a joke that there's a famous conference in NLP called EMNLP. And a few years ago, that stood for Embedding Models in NLP, because there were so many embeddings papers. But now things have cooled down a little bit, and there's less of a focus on word embeddings. But so limitations of embeddings, there's a lot of them. One is that they're still sensitive to superficial differences, like dog and dogs, especially for less common words. Another thing is that they're insensitive to the context in which the word is used, so financial bank or bank of a river. Another thing is they're not necessarily coordinated with other sources of knowledge or across languages. And another one is that they're not interpretable on their own. So as I mentioned before, each of the dimensions might not necessarily mean something. Another thing is that they can encode bias. So one thing that people have been interested in recently is they encode, for example, stereotypical gender roles or racial biases as reflected in our data. So one way to get around this is to do subword embedding. So subword embedding basically looks at the characteristics of the subwords. And this is a relatively early attempt to do this. This was with recursive neural networks. So they're kind of tree-structured neural networks, and the way they work is with by combining together morphemes in the word in order to get the final embedding for the word itself. And this is a good idea because the meaning of words is compositional. So unfortunate will be some combination of unfortunate, etc. Another way that's a little bit like you don't have to make as many assumptions about the data that you can get for the language. You don't need to assume that you can get a morphological analyzer like this for the language. Is just running a bidirectional recurrent neural network, which I'll talk about in a few classes, over this and grabbing the last state of the network to create a word embedding. And this was done by Wang Ling, who is here at CMU. For subword embeddings, another way, this is popular in nowadays because it's used in fast text as kind of their default model, and is bag of character n-grams. So this is a way of representing words. This was actually also made by John Weeding, who is also here at CMU. So we're doing pretty well on the subword models for word embeddings, 2 out of 3. So we have where. So what we do is we basically find all of the character n-grams that exist in this, and we add them together, and we get embeddings for each of these. So we get embeddings for like beginning of sentence WH, W-H-E, H-E-R, E-R-E, R-E. And we treat the embedding of the word as basically the sum of these. And the reason why this is useful is this is really efficient to calculate. You just need to look up the n-grams and add them together. But it's also a good way to kind of get subword information, not just information about the word itself. So that's all for subword embeddings, which solve the problem of not considering word form when we're calculating our embeddings.
In subword embeddings,
Uh-huh.
there is also, when you say each of the character n-grams you're taking, is there any other input for the word? Like in case of where HER appears in a lot of varied contexts.
Yep.
So will it not dilute the actual context of like how where appears?
So the way this method works, it does not. And the basic thinking behind this method is it uses 3 to 6 character n-grams of length 3 to 6, and then one embedding for the word itself. So for really common words, it will just remember the embedding for the word itself. For less common words, but still pretty frequent, it might remember some of the 6 grams.
So it's a mixture of both.
Yeah, it's a mixture of both. And by combining them together, you can kind of generalize at the appropriate level. Okay. So the next problem was that embeddings are insensitive to the context that they're used in. So things like this example is position, and there's lots of meanings of position, like location, post, etc. I guess position in a game, in a sports game. And if you take the average of kind of all of these embeddings, you're going to get something that doesn't really make a whole lot of sense. You're going to get something that reflects all of these meanings, and it's going to be put in a place in the space that's not very consistent. So there's been a reasonable amount of work in various in various models. One example of this is this Reisinger and Mooning paper that allows you to basically split your embeddings for a single word into different embeddings for each of the meanings. And there what you try to do is you try to keep it as close as possible to the original, but as faithful as possible to the senses that you're trying to represent. You can also do things like non-parametric estimation. So the idea is you don't know ahead of time the number of senses that each particular word will have, and you predict the number of senses on the fly by basically splitting things apart, seeing if you get any gain in your accuracy, and then merging them back together if you don't get any gain. And there's other methods to do this as well. So the next thing is coordination of embeddings. So this is a useful tool. This was also made by Manal Faroukhi here at CMU. So we have word embeddings in 2 languages, and we would like these to match across languages. So the basic idea of what they do here is for each language, we have a subset of embeddings that exist in some dictionaries. So the dictionary tells you this word translates into this word. And then we try to learn a transformation matrix that combines the words across languages so that the words are that the words that translate into each other are as close as possible in embedding space. So in this particular case, they used a method called CCA, canonical correlation analysis, but there are other methods to do this as well. And there's actually a survey that just came out that I forgot to post on the website, but I will try to do, which is a survey of cross-lingual embedding methods, and there's like 20 or 30 different methods cited there that you can take a look at. And one of the interesting things is that coordinating things across languages doesn't just give you things that are consistent across languages, it also improves your accuracy altogether. And the reason why it improves your accuracy altogether is because things that might look very similar in context, like beautiful and ugly, tend to appear in the same context. Love and hate tend to appear in the same context. But if you translate them into a different language, they'll, of course, translate very differently. So as a result, you get a better embedding space in each language itself as well. One very hot topic recently is unsupervised coordination of embeddings. So the idea here is the previous method tried to map embeddings based on a dictionary, and you need to have a dictionary in the various languages. But what if we don't have any dictionary and we just know, we just have a big corpus of English and a big corpus of or French or something? We have big bilingual corpora of English and French, but let's say it was English and French. Can we map without actually even knowing any of these? And the answer is yes, we can do this surprisingly well. It's actually a very surprising result. So one simple way that works is we just use the words that are identical across the languages. So for example, we just use the digits, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's a large enough dictionary to actually allow us to do embedding, cross-lingual mapping of embeddings. Another even crazier idea is the distributions of the embeddings should look similar across the languages. So words that are common in one language should be common in another language. And based on this, you can kind of get this very, very rough mapping between the languages where the common words tend to map into other ones, and you learn a transformation matrix based on this. The first really successful method for doing this was by Zhang et al., and they used a thing called Earth Mover's distance. And Earth Mover's distance is basically the amount of distance that you need to move probability in a distribution in order to get the two distributions to match exactly. And they learned a transformation matrix so that the Earth Mover's distance between the two distributions was as low as possible. And they used a technique, which I'll talk about later, but I think a lot of people know about, which is like adversarial it's adversarial learning, and this is an instance of the Wasserstein-Gann, if you're familiar with that. But I think this is a very interesting method that I would have never thought worked, but it actually works pretty well. So another thing that, I think I have like 2 more slides maybe. So another thing that you can do is you can try to get the vectors to match lexicons. So like, let's say you have a lexicon like WordNet. This has a lot of information that people have built over a long time, or something like a Wikipedia or Freebase, where you have all these links between things that you would like to use to improve your word embeddings. And there's basically an idea that if we have all these things with links, we will want things that are linked together as synonyms to be closer together in word embedding space. So they formulated an objective, which is kind of small down here, which has 2 parts. Basically, for any word I, we want it to stay as close as possible to its previous place in the embedding space. So we want to not change it very much. And then we also want it to be close to all of its neighbors. So all of its synonyms, we want it to be as close as possible. So this is a simple thing, but it's good at using existing resources. And it was a class project here at CMU, and it won Best Paper Award at NACL, apparently. So, yeah.
Do they look at doing this for like antonyms and
yeah.
relationships?
So the question is, did people look at doing this for antonyms? And the answer is yes. People have looked at doing this for lots of other relationships. There's a paper explicitly tailored to antonyms, and then there's also papers that cover all different knowledge-based relations, which I'll be talking about later in the class, I guess. Yeah. Okay. So the final one is about interpretability. So I had a question about whether the dimensions are interpretable, and I'm finally returning to that question. So basically, each dimension of the word embedding is not interpretable normally, unless you do something like dimension reduction. But there are solutions, and the main solution is to add kind of a sparsity constraint. where you learn sparse embeddings. And what this means is most of the dimensions in the embedding are 0, and all the other dimensions are non-zero. And if you do this, because you're enforcing the dimensions to only be active in some cases, each dimension tends to be more interpretable. So this is one way to solve this problem. Yeah, and Danish is the person to ask about that, I guess, because he has a nice model for that.
No, so, is this as simple as adding like a L1 regularization term to your loss, or?
This one, I believe that's what they did, but I don't remember exactly what they did. So, yeah. Okay, sorry, I have one more slide. I said 2, but I have 3. So the final one, this is kind of important nowadays when people are very interested in the implications of building systems. So you go out to a company, you build a big system that affects lots of people's lives. And you want it to affect their lives in a positive way and not a negative way. And what people have realized is that word embeddings reflect bias in statistics. So one example is if you take occupations and you say extreme she, it tends to be things like homemaker, nurse, receptionist, librarian, socialite. And for he, it reflects things like maestro, skipper, protege, philosopher, and captain. And these are kind of traditional things we think of as traditional gender roles. A long time ago, this was often the case that there was a lot of bias in the way people did gender, considered occupations for gender. But we're trying to move away from that and be more egalitarian in everything. So if our models are biased by word embeddings, and these word embeddings reflect the biases that we used to have but probably should not have, then it would be a good idea to ensure that our word embeddings weren't accidentally doing this. And for things like non-discrimination in choosing loans, for example, this is actually legally mandated that we're not allowed to discriminate. So this is an interesting paper on doing this. And basically what they did is they identified a few pairs that shouldn't be biased. And like, for example, gender roles or whatever, occupations or whatever. And they find a direction of the trait to neutralize, and like male and female, and they ensure that word embeddings that you want to not encode bias are neutral in that direction. So this is not the only way to do this, and I'm sure there are lots of better ways, but I think this is something important to think about, especially if you're building systems with implications. So that is all for word embeddings. And sorry, I'll try not to go over class. I went over by 2 minutes today, but if you have any questions, I'll be happy to answer them afterwards.